Welcome to this explainer, everyone. Today, we're untangling a cosmic mystery surrounding two fundamental concepts of science. You've probably used these words interchangeably your whole life, but today, we're going to see them in a totally new, surprisingly literal light.
So are mass and weight the exact same thing? I mean, we use these words interchangeably all the time, right? You step on a scale at the gym and say, I weigh this much, or you look at a box of cereal that says net mass. But in the rigorous realm of physics, they actually represent entirely different physical properties. Conflating the two is honestly one of the most common scientific misunderstandings out there. To clear up this confusion, here's our roadmap for today. First, we'll meet your mass. Then we'll look at the force of weight. After that, we're comparing Earth versus space, and finally, we'll connect mass and weight. All right, let's dive right into section 1. Meet your mass, the amount of matter. Mass is, quite simply, the amount of matter in a body. The crucial point to remember here is that mass represents the absolute physical stuff. It's the atoms, the molecules, the tangible reality of a thing. It doesn't care where it is in the universe. It's literally just a measure of what is actually there. Now, to measure this physical matter accurately in a lab, we use a standard balance scale. The mechanism is pretty clever. It compares an object on one side against known standard weights on the other. Because it's a direct comparison of physical matter against physical matter, it tells us the true, unchanging mass of an object. When we record that measurement, the standard scientific unit we always use for mass is the kilogram. This lets us definitively say, for example, that a bunch of bananas consists of exactly 1 kilogram of matter. Or, a heavier bag of groceries might have a mass of 2 kilograms. It's an absolute universal measurement of the matter present. Moving right along to section 2. The force of weight, Earth's attraction. So weight is the force of attraction exerted by the Earth, or really whatever planet you happen to be standing on a body. Unlike mass, weight isn't about the amount of matter you have built up inside you. Instead, it's the localized gravitational pull dragging that matter downward. It's a dynamic, active interaction between an object and a planet. Because weight is an active force rather than a static amount of matter, we actually have to measure it using a completely different tool called a spring balance. Instead of comparing stuff to stuff on two sides of a scale, a spring balance simply lets gravity pull the object down, which stretches an internal spring. The harder gravity pulls, the more that spring stretches. Furthermore, weight is measured in newtons. Think about what this actually means. When you step on a standard bathroom scale, you aren't actually measuring your mass. You are measuring the newtons of force your body exerts on the ground. The scale is basically just politely translating that force into kilograms or pounds for your convenience. A given stone, for instance, might exert a downward force or weight of 2.5 newtons. Which brings us to section 3, Earth versus space, where location really matters. Let's run a little cosmic thought experiment here. Say our bananas possess exactly 1 kilogram of mass on Earth. Now, what if we take those bananas to Mars? They're still exactly 1 kilogram. The physical stuff inside them hasn't changed one bit. Mass is an absolute constant, no matter where you travel in the universe. But consider an astronaut. His mass stays at a constant 120 kilograms everywhere he goes. But his weight? On Earth, strong gravity pulls him down with 1,200 newtons of force. On the moon, that plummets to just 200 newtons. The force of gravity changed, so his weight changed, even though he literally didn't lose a single atom of his actual body.
And this brings us to our ultimate takeaway. Mass, measured in kilograms, is your constant physical reality. It's what you're made of. Weight, on the other hand, is measured in newtons and is merely a localized gravitational reaction. It varies entirely depending on your location and altitude.
All right, let's wrap things up with section 4, connecting mass and weight, the mathematical link. We can actually unite these scientific siblings with an incredibly simple calculation triangle. Weight, in newtons, simply equals your mass in kilograms multiplied by g, which just represents the gravitational field strength of wherever you happen to be.
So here's how we apply it. Step 1, grab your mass in kilograms. Step 2, identify the gravity. On Earth, gravity exerts roughly 10 newtons of force for every kilogram of mass, so g is essentially 10. Step 3, just multiply them. If we have a 5 kilogram object, we multiply 5 by 10 to instantly discover a downward weight of 50 newtons. Simple, right?
Now, a quick mathematical pro tip to keep your calculations perfect. You've got to always convert grams to kilograms first to get an accurate Newton measurement. For instance, 14 grams must become 0.014 kilograms, which then multiplies by 10 to give you 0.14 newtons. And by working backward with this triangle, you can also easily divide weight by gravity to reveal true mass. If a rock weighs 3.5 newtons on Earth, dividing by 10 tells us its mass is 0.35 kilograms.
I'm going to leave you with this final kind of mind-bending question. If you float out into deep interstellar space, where the gravitational pull from any planet or star is 0, do you physically disappear? Well, looking at our formula, your weight would absolutely drop to 0 newtons, making you completely weightless. But thanks to the stubborn, unchangeable nature of mass, your physical matter, the absolute stuff that makes you, will always exist. I really hope you've enjoyed mastering these concepts in this explainer today, and remember to keep asking fascinating questions about the universe.